Okay, and we are doing this. All right, so we're going to just finish up section 1.2 today, and then you're going to do all the practice for 1.2 so that you're ready for the quiz, which is tomorrow. Okay, it won't be very long. All right, but there we go. All right, and we don't want Chem 11, we want Chem 12. And we need to go to page 36. Okay, so in Chemistry 12, you are not required to explain differences in reactivity due to the nature of reactants, okay? But you should recognize when the nature of the reactants is the thing affecting the reaction, okay? And that would be when you have similar but somewhat different reactants. Now, during chemical reactions, chemical bonds are broken. That's how we break up the reactants. And then new bonds are formed. So the reaction is going to go faster if we break up our chemical bonds faster. So if it's easier to break the chemical bonds, the reaction will go faster. If it's harder to break the bonds, the reaction will go slower. Because if the bonds are hard to break, they will require a lot of energy.
I'm going to Mountain Madness.
Do you have the form?
The form.
You need a form. So you might want to go get a form.
Where?
I don't know.
Okay.
Okay? Yeah. All right. So that would require a lot of energy to break those bonds. So that means that that energy hill will be tall. Yes? But if the bonds are easy to break, that's going to require only a little energy. Whoops, what did I just do? In that case, the peak is going to be really small. Okay, this pen is driving me crazy. It starts writing, stops writing. No. Okay, here we go. Okay, so it's going to have a little hill. And so more collisions will have enough energy to achieve that peak. So what kinds of reactions tend to have little hills? Well, let's take a look at reactions that involve ions in solution. Here we have barium 2+ and we have chromium 2-. What do positive and negative do to one another? They attract, absolutely. So positive attracts negative. So under normal circumstances, you could have molecules kind of wandering around. You remember like the blindfolded people in the classroom? Yes? Okay, and so maybe occasionally they'll run into each other. But when you have a positive and a negative, it's as though two of the particles are attached by a string and you kind of pull on that string and it makes it easier to find the opposite charge. Yes? So that is one of the things. So when we go down here, why are double replacement reactions in particular? They are very quick. Why are double replacements so quick? Well, the first reason, and this is the one we just talked about, is that we have the positive and negative charges. They attract. So particles don't just have to randomly collide. They are drawn together by that attraction. Now, there's another reason as well that ions in aqueous solution are quick. Whoops, sorry. They're faster than gases. They react faster than gases. Can you think of a reason why? If I was to draw some gas and try and show you the particles, yes? Because gas is mostly empty space. Okay, there's a few little particles here and there. I'll make them a little bit bigger so you can see them a little bit better. But really, it's mostly empty space. If I was to draw my gas on the board, I might be like, oh, there's a particle down here. There's another one over here. And then there's one over here. But all the rest of it's really empty space. Yes? But if you have aqueous, now what you've got is you've got the particles are much closer together. And if the particles are much closer together, what can we say about the probability of a collision? Probability of a collision is higher. Okay, so two reasons why double replacement reactions are probably the fastest of all reactions. Number one, the aqueous particles are quite close together. Therefore, probability of collision is higher. Second reason is in a double replacement reaction, you're always going to have a positive combining with a negative. So we don't just have to have random collisions. We're going to have the particles pulling towards each other. Did you not manage to get a form? Pardon me? Oh, okay. That's a bummer. Do you want to just finish the lesson and then go? Okay, so particles are, probability of the collisions is higher, blah, 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 blah. Okay, so let's go back then to our redox reaction. I'll give you a second to finish writing that if you're still writing. Okay. And then we're going to go back up here because this is a double replacement, but it is the net ionic form. So it's really easy to see the positive and the negative ion, yes? But what if I gave you the double replacement reaction and I gave you the formula equation? Are those positive and negative ions still in there? Yes. All we've done is we've hidden the ions, okay? We've hidden the positive and the negative. So if you're looking at these, and usually what will happen is you'll be given a bunch of reactions, say multiple choice, 4 reactions, bing, 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 and you're asked, which is the fastest? All right, you might be looking and you're like, oh, I know that ions in solution are the fastest. And I know that double replacement is the fastest of the fastest, right? But you might look at this and you might be like, I don't see any ions. And you'd go, oh, that one's not so fast. But don't forget, we really have barium 2+, and CrO4 2-. So we do have those ions in solution, okay? So don't miss the hidden ions. So double replacement is the absolute, the very fastest. Other ions in solution are also fast, but not quite as fast as double replacement. And we'll take a look at why. So if we go down here, we're going to see, oh, look, I've got some ions in solution down at the bottom of the page. But what I've got is I've got 2 manganese, yes? And I have 5 H2SO4s. How many reactant particles is that altogether? 2 + 5 is 7 reactant molecules. The more reactant molecules that have to collide, do you think that's going to make the reaction faster or slower? Slower. It's going to make it slower. So the more reactant particles that need to collide, the slower the reaction. So these 2 reactions are still fast, but they're not as fast as a double replacement. And again, you can see in this second reaction here, we've got 6 F2s, we've got 1 Cr2O7, and we have 14 hydrogens. How many is that all together? It's like 21. Okay, that's a crazy number of particles, right? 21 reactant molecules. So that's going to be slower, but still faster than a gas because the particles are closer together. Yes.
What if a double replacement has a lot of reactants?
There won't be that many. The most you would have is like 5. Because you would end up with 5 if you had like a 3:2 ratio. So if you had Fe3 plus and let's say CO3 2 minus, those would combine in a 2:3 ratio. So yeah, you can just say if it's double replacement, it's going to be the fastest. The other thing that the double replacements have going for them is that positive-negative interaction that drags the particles together, okay? As opposed to, these other ones. Here we've got a negative charge and a neutral, right? So not quite as much. Here we've got a whole bunch of positives, a whole bunch more positive, and then just a few negatives. So again, they're not being dragged together in the same way, okay? All right. So that deals with our aqueous ions, usually the fastest. Second is that if you have a solid, they are much slower than aqueous, liquid, or gas. And why is that? How do the particles in a solid move? If I was in a solid, I'm one of the particles, do I go zipping about? No, I just sit there and right? That's all solid particles do. They just jiggle. Yes? They just jiggle. So they are less likely to collide. So usually solids are the slowest. Actually, I should say solid reactants. These are generalizations. There are some reactions where you have a solid reactant and it's quite quick. Do you remember one from yesterday? Right? So these are not like tried and true, but I'm not going to give you any non-obvious ones. Okay, I'm only going to give you obvious stuff. Now, the last one is that the breaking of covalent bonds is quite slow. And that is because covalent bonds are very strong. And if a bond is very strong, how much energy will it take to break it? It'll take a lot of energy to break. And therefore, the activation energy is very high. That energy peak is very tall. So the activation energy, which is the energy required for a collision to be successful, is very high. We have a high activation peak. Why does a high activation peak make the reaction slow? Tell your partner, why does a high activation peak make the reaction slow? Okay, why? It requires more energy, and that means that a smaller percentage of collisions will have enough energy. So a smaller percent of collisions will have enough energy. How are you going to know that you have a covalent, that you have covalent bonds that need to be broken? I'll let you finish writing, then I'll ask it again. Because I got people writing and of course you don't hear when you're writing. How do you know if you've got covalent bonds? Yes. Yes, you got to have non-metal plus non-metal, okay? So here we have non-metal, and we have another non-metal, and therefore it's going to be covalent, okay? Which means it's going to have a high activation peak because the covalent bonds are very strong. And I am done with my lesson for today. So I'm going to just let you work for the rest of the period because your quiz is tomorrow and there's like a lot of review to do. So I'll let you know which pages to do and which questions to omit. Okay, it is on Teams. If there are any of you who would like to go down to Mountain Madness, you're supposed to have a permission form, but you know, just don't tell them you're from my class. Okay, just be like, oh, I didn't know I had to have a form. So if you do want to go down, that's fine. If you want to stay here, we will be working on pages. Let's see, it's on Teams. Chem 12. I'll write it on the board so we can see it. Oh, no, here we go. Okay, pages 37 to 50. But you can omit, from pages 43 to 50, you can omit numbers 1, 2, 4, 8. C, 15, 17, 18. There we go. Now, do you have to do every question to be ready for the quiz? No. But do a selection. You should probably hit page 50 because there's a few questions on there that are different. But like, you know, if one question looks just like the next question and you're like, oh, I just did one like this, then skip that one and come back to it later if you have time. The reason we're omitting these ones is because they are about monitoring the rate and calculating the rate, which you already did your quiz on. You can go back to these later before the test if you want to review that later. Okay, but for now, just let them be because you just wrote the quiz on that already. Okay? And that's it. So now is a good time to ask questions, all that good stuff. Yeah.
Actually, we did pages yesterday.
Okay, so you're done everything. Okay.
Yeah,
Okay.
This one's the thing. Oh, is this the same question or is this the type?
Oh, yeah, that should say if you increase the
Oh,
volume.
okay.
That's page
Then it's gonna
38.
be different.
Yeah.
That makes sense.
Hi.
I just wanted to verify I did everything correctly as well as like just get out all my questions because I'm so busy today and tomorrow. So I did all the homework.
Yes.
Yesterday, and I was just wondering if like what I wrote was like correct.
Have you checked your answers
I
with the
checked
answer
it,
key?
and,
Okay.
like, times. Like, I wrote it like really quick. Like
Yes, I can tell. I can hardly read that. Okay, so what are we looking at here?
so. This
Which ones would you like me to look at?
This is just some like so for the 6 factors, right? You need like concentration, volume, temperature.
Yeah.
You need to know all of those. Are guaranteed.
Yeah.
The first 4 factors. This one I was a little.
Uh-huh.
Do we need to
Well,
know
if you
like
look-
the first?
You know, I just didn't want to give you the answer to this one in this question. Okay? Yeah.
We won't need to know about the first 4 factors, like frequency.
No.
And then same for B. Well, I think B's a little obvious, but like, well, I need to like know that.
Affects the percentage of collisions. Temperature. Yes.
Calculate that.
Which of the first 4 factors listed on page 1? Frequency and the percent of collisions. That would be temperature, yeah. Yeah.
And surface area.
Surface area only, yeah.
Also, it's only surface area, but that's not.
Well, all of them affect heterogeneous reactions, but this one affects only heterogeneous reactions. It does not affect homogeneous reactions. So temperature would affect both heterogeneous and homogeneous.
But everything else.
Concentration would affect homo and heterogeneous.
Mm.
Yes?
Okay.
But if you change the surface area, that's only going to affect a heterogeneous reaction. Because homogeneous reactions don't have any surfaces. Yes, you cannot change a surface area if there is no surface. Yeah?
I-
Okay.
For number 6, right?
Uh-huh.
I did it my own way because I didn't understand how the answer you wrote.
Okay.
I was a little
So what did
stressed
you
up
say?
on that. I guess essentially you just shrink the space.
Okay.
No, you increase the amount of like people in the space.
Okay,
and that
yeah.
means more collision as well, right?
That's it.
Okay, and then these ones, continue plenty of gas. Oh, yeah, these are-
Yeah, this should say increase
yeah, I think.
because I made a typo.
Yeah, I'm not so nice.
Okay, we're gonna take a break
Okay.
and then I'm gonna answer these.
Oh.
Hi. Yes. We had paid for lunch. Let's see, May. Julie, there you are. Good stuff. On the quiz, I haven't made it yet.
Oh, sure.
So, yeah, it won't be very long. Yeah.
Yeah.
Oh, yeah, 6 days.
Only like, subtraction, not division.
Yeah, we have.
The whole thing? Now, so. What's the gigs? Multiplying and dividing, adding and subtracting. Adding and subtracting. So you. My sister filed this. Okay, yeah, I don't want to.
And they don't increase it just.
But you know what you do? You just borrow it and then just like do the questions.
Exactly, yeah.
Right? So you can just.
You came off of it.
Yeah, I'll give it back to you. Yeah, no worries. Here, after you, after you.
I think it's run hard. Yeah. Okay.
Yeah.
That are mixed.
I wrote it on one.
Yeah.
Did it on two.
Yeah.
You can tell.
And then, and they're gonna do it.
What's that for the phase? What's that for some logic here?
It's good.
Well, it's like, it's reactants that are in phase. They're in phase. So like, you have phase, there's one, right? First semester last year. So the reactants.
Phase. Yeah.
That's a long one.
Phase power.
How's it going? Oh, okay, so you're reading it, and don't watch the video, read it.
Oh, I like it.
Ready?
Yes.
It's the same thing. Yeah, phase and bonding reactions. I did like one phase.
Okay, a phase is a homogeneous area. Okay. So if you have an aqueous solution, that is a phase. A phase is an area of the system where all the properties are the same, all throughout the system.
So let's see, I got like two mixtures combined with one. One of the two mixtures, like the same thing as one, this is a phase.
Yeah.
Or you combine the two, that one minus reaction. Or do it together to the one reaction.
As long as there is only one phase. Homogeneous reaction is one where there's only one phase.
I forget this. So let's say I have quickly here, we go to the phase. So this would be a phase. The whole thing would be a minus reaction. That would.
So.
Let's be like, let's say to this now.
I don't think it's that big a deal. I think they're overthinking it. Phase, phase. Non-homogeneous. Is this all the same? No, we have sponge phase, we have water phase. Yes. Two different phases. Okay? It's not all the same. This has the properties of a sponge. This has the properties of water. Now, if I took some salt and put it in here. Right now, two phases. Now, we're gonna ignore the slope that's still at the bottom. And the fact that there's bubbles and like it's doing it. It's not homogeneous reaction, it's homogeneous mixture. Okay. Now, if I was to pour something else in here that was also aqueous, that's homogeneous because they mix the both. Okay? So if I have some acid, aqueous, and some base, aqueous, and I pour them together, is everything in the same phase? Yes. Because look, here's some acid. Come with me. If you give it a stir, are they mixed?
Yes.
Then it's about to be mixed reality. Don't talk about not giving a stir. Okay? It will they mix if they are given a stir, then yes, it is not. If I stir that sponge, it's gonna mix with the water. No, it still stays sponge. Okay? Yeah. Okay.
Okay.
How are we doing? Anyone have any questions?